Hi, welcome back to Drafting 112 at Blue Mountain Community College. Today I want to talk to you about tolerancing and fits, and this is chapter 7 in your textbook. And tolerancing is something that you as a designer drafter can really collaborate with the engineer on. Engineers don't always live in the world of tolerances and fit. And so they might not, they might know they want a close fit, or they know what they want the part to do, but they might need some collaboration in specifying the actual tolerance. And so this is an area that you as a drafter designer can really participate in and assist those engineers in their design. So let's get to my screen, and we are going to spend some time talking about tolerancing nomenclature so that you know what these marks that you're putting on these drawings mean. And we're also going to talk about how we designate tolerances and understand ANSI, and we'll talk about what ANSI is. It's an American National Standards Organization, as well as ISO, which is the International Standards Organization. Fits. And we're going to use some AutoCAD tools also. So let's go ahead. This chapter actually builds pretty closely onto what we just talked about, chapter 6, which is why they're in the same week together. So let's talk about precision and tolerance. And precision is really an indicator of how close to a specified measurement a feature of a part needs to be. So you can think of precision as, if you're thinking about target shooting, precision is how close to the bullseye you are. And so sometimes we confuse that with accuracy. Or it's a measure, precision actually is. Precision is the repeatability. Yeah, we're not going to go into that. What we want to understand is that tolerance is an indication of how precise the machining on the part needs to be. So for example, in this part that we've got shown right here, there's a few pieces of this drawing that I want to talk to you about. If we look at hold on, there we go. If we look at this guy right here, this gives us the tolerance, or the precision, rather the tolerance, for this notch opening. What this tells us is that this notch opening needs to be no more than 1.375 inches and no less than 1.370 inches. So this thing has got, we don't have a nominal dimension indicated, and we'll talk about nominal in a minute. What we've got is a maximum and a minimum. So this is one style of tolerancing. What this doesn't give us a plus or a minus from a nominal. What it says is, as long as you are anywhere between 1.625 and 1.620 inches on this vertical dimension, your part is within acceptable measurements. Down here we've got a kind of a standard boilerplate sort of statement. This usually appears in the title block of your drawing, and what this says is that if there's any measurement on here, for example this one, that does not have a minimum and a maximum indicated, then it will comply with the standard tolerances of plus or minus 1/64 of an inch. And angles, if they are not otherwise indicated, are plus or minus 1 degree. So we've got both some specific limits and some generic limits that apply to the entire drawing. Okay. There are different ways that we can specify tolerances. We can stack them one above the other. So this is the limits. In other words, we've got a maximum size of 1.375 and a minimum size of 1.370. The maximum size goes on top, the minimum size goes on the bottom. We can also put these on a single line, and this says that this dimension can be anywhere between 1.375 and 1.372. So again, the maximum and the minimum. These are both examples of limit style tolerancing. In other words, we have specified the limits of the size that is acceptable for this part. If we use a single line, we want to be sure and put a dash in between the two numbers. Okay, the other thing that we can do is what's called bilateral tolerancing. And what this does is this gives us that nominal size, so a target size of 1.750, and then an upward variation of up to 0.003 inches, and down to 0.00, and as much as 0.002 inches less than that number. So what this really says is 1.753 to 1.748. In other words, 1.75 plus 0.003 to 1.75 minus 0.002. This is the style of bilateral tolerancing we use if our tolerances are asymmetric. You'll notice we've got a slightly larger allowed variation in the plus than we do in the minus. Now, if they are symmetrical, if plus and minus are the same, then we can stack the plus and the minus together and just write this as 1.750 plus or minus 0.002. Okay, sometimes we'll have variation only in one direction. So, for example, up here, we've got 1.375 plus 0 minus 0.002. What that means is that my hole can be, or my dimension, sorry, whatever dimension this is, can be no more than 1.375 inches in length. But we can tolerate something as small as 1.373. It's exactly like it says. We can also have variation that's not only allowed in the upward side. So this is another example, 1.75 plus 0.03 minus 0. That means this dimension here must be at least 1.750 inches and no more than 1.753. Fairly straightforward once you know what you're reading. We already talked about these general tolerances. And all of this information is in your textbook, again, in Chapter 7. Okay, there's some nomenclature that we want to be familiar with. Nominal size, I've been talking about that as I've talked about the nominal size. It's the designation used for a general identification. A very common example of this is pipes. If you've ever bought and worked with piping at all, you will know that a 2-inch pipe is not 2 inches in diameter, either inside or outside dimension. So a 2-inch pipe is an example of a nominal size. Another example is a 2x4. If you've done any construction, you know that the piece of lumber that we call a 2x4 is not 2 inches in any dimension, nor is it 4 inches in any dimension, but its nominal size is a 2x4. The actual size are the sizes that we would actually measure. So for example, on that 2x4, I think it's down to 1.5 by 3.5. It used to be 1 3/4 inches by 2 3/4 inches. Maybe that's what it is. But regardless, the actual size is whatever that lumber actually measures. The basic size or basic dimension, that is the size or dimension that is the important feature of the design. So this is the basic thing from which we define other things. And sometimes, especially in mated parts, you'll need to know which part is going to be the basic size. We'll talk some more about that when we get to holes and shafts later. Fit. So I'm down here on fit. The fit is really how tightly do these things have to fit together. Think, for example, of drawers going into their slots. How closely do you want that back part of that drawer to be to fit into its hole. You want some room for it to run in and out, but you don't want it so loose that it's sloppy. Same thing goes for axles or even shafts that are fit into holes and provide a permanent join. We got to talk about how closely those things need to fit. The allowance is essentially the minimum clearance space between two mated parts. For example, gears. There's always a certain amount of space between the teeth. That would be the allowance. And tolerance we've already talked about. Now, this MMC, maximum material condition, this is the choice of limits, either upper or lower, in which the size of the part has the most material. So this is a little bit misleading because if you think about a hole, the maximum material condition is going to be the smallest allowable size of the hole, right? But if you think about a shaft, the maximum material condition is going to be the largest allowable shaft size. The least material condition is exactly the opposite of the maximum. It's the limit that gives you the least material in that part. So for holes, it would be the maximum size hole. For shafts, it would be the smallest allowable shaft size. Okay, so let's talk about tightest fit. Now the tightest fit, if we think about this for a minute, is going to be the minimum tolerance, or the minimum clearance rather. So what this means is it's the largest allowed shaft going into the smallest allowed hole. So if we look at this drawing right here, the tightest fit, our smallest hole is 1.125, and our largest shaft is 1.124. So if we take the difference between those values, we're going to get the smallest allowed clearance, which is 1/1000th. Okay? So that's the tightest fit between these two parts. It's fairly tight. Okay, the loosest fit, on the other hand, is going to be the smallest shaft going into the largest hole. So back there in Chapter 6, we talked a little bit about tolerance accumulation. This is another variety of that. We have to think about the extremes in both conditions, either tightest fit or loosest fit. So in this case, our loosest fit is the largest hole, which is 1.127, and the smallest shaft, which is 1.121, or a clearance of 0.006. Now the reason why this all matters is because nothing is ever going to be machined or manufactured to exactly the size that we specify. So what our quality control is going to be is to check to see if these parts are within our measured tolerances. And so we have to understand how our tolerances have the potential to impact fit. This is particularly important in these days of automated manufacturing because the lowest manufacturing costs are going to split the difference between precision and sloppiness. Okay, so let's look at an example here. And I want you to pause this lecture and actually work this out before you go on to look at the answer. So we've got the size limits of two mating parts are shown below. And I want you to actually take a minute with pencil and paper to figure out the nominal size of both the shaft and the hole, the tolerance of the shaft, the tolerance of the hole, the allowance, and the maximum clearance. Okay. Pause this lecture, look back through your notes, and see if you can figure all those things out. Let's go ahead and take a look at the answer. So, the nominal size is 1.25, and we know this because we've got 1.25 and 1.25. and my shaft rounds to 1.25 and 1.25. So to find your nominal size, especially on something like this that isn't a pipe or a piece of lumber, you look for the value to which everything would round, 1.25. The tolerance of the shaft is the maximum allowed size minus the minimum allowed size, which is 0.003 for the shaft. Okay? So the shaft, we'll talk about that in a minute. Now the tolerance for the hole is the maximum hole minus minimum hole, which is 1.2504 minus 1.2500, or 0.004. To be aware, there is a typographical error right here on our slide. It should be 1.2496. Sorry, give me just a second, I'll silence that. They did the math correctly. 1.2496 minus 1.2493 is 0.003. They just have a typographical error right here. Okay, now our minimum hole, or rather our allowance, is the minimum hole minus the maximum shaft. This one I have to take. I'll come back and record this later. Hey, sweetie.